I want to thank the organizers and IPAM. I've been involved with IPAM since like 2004. I've organized long programs, short programs. When I wasn't in academia, I was an industrial mentor for their research in industrial partnership program. So IPAM is a gem. So thank you very much for hosting this. I know how much work goes into these things. So today I'm going to talk to you guys about this work that we did on what's called task-driven network discovery. And the fact that we used a deep reinforcement learning model becomes clear as we go along, but the idea was really to focus on this task-driven network discovery. The work is a joint with Dr. Rajmonda Caceres, who's on the participants list. Thank you, Rajmonda, for attending the talk. If I say anything wrong, and she can correct me. Rajmonda is at MIT Lincoln Laboratory, and our colleague Peter Morales, who was at MIT Lincoln Laboratory when we did this work and then moved to Microsoft earlier this year. And the work is forthcoming in the Applied Network Science Journal, part of moving to the Network Science Institute. Now I publish in Network Science Venues, which is fun. Okay, so complex networks are ubiquitous. If you haven't drank the Kool-Aid, call me, I'll send you the Kool-Aid, right? You're interested in some phenomena, either social or physical or technological, and you know that there are relational dependencies between the entities. And so you want to learn predictive and descriptive models of the complex topology that connects the various elements, right? From technological networks to social networks, information network, biological networks. Now, there is a lie, there is a falsehood on this slide in that partially observed complex networks are ubiquitous. Fully observed complex networks are not as ubiquitous as you would like them to be. So whatever phenomena you're interested in is oftentimes partially observed. For example, right now, we would love to have the fully observed contact network, right? To be able to do tracing and controlling the pandemic. There's also oftentimes hard in terms of hard or expensive in terms of collecting more data. And the last thing is, even if you had all the data in the world, you may not have all the computational power in the world. And even if you did have all the computational power in the world, you may not want to use it for climate change purposes, or you just, you'd rather not use all the computational power in the world. So, and of course, we all know that when you work on partially observed or incomplete data, your analysis can be skewed, right? So if you have the graph on the left, and I ask you to give me the average degree, you say, oh, well, that's easy. 2 times the number of edges divided up by the number of vertices. The answer you're going to give me is going to be incorrect. Because the omniscient being has the fully observed network and says, well, that's wrong. Now, the one thing, this is just an explanation mark here. Before the pandemic, I visited CDC and I met with some folks at a clinic in San Francisco where they were interested in expanding the social network that they had in terms of people who have sexually transmitted diseases. And so one of the things that I found out was that your missing data is not missing at random. And so we oftentimes assume that, okay, fine, I have incomplete data. But, however it is incomplete, it's missing at random. And that, of course, helps in terms of having proofs and bounds and so on and so forth. But in reality, data is not missing at random. So, for example, if you're tracing sexually transmitted diseases, oftentimes you hand coupons to the communities that you're interested in. They come into the clinic and you ask them about the last 3 sexual contacts, and they could lie, they could not tell you the truth, they could do lots of different things, right? And so your data is not missing at random. But the question that we wanted to answer was the following question: given a query budget for identifying additional nodes and edges, how can one get a more accurate representation of the fully observed network? So that's the network discovery problem. You may have heard about it in terms of network completion. You may have heard about it in terms of, well, I kind of know what model is producing my data. I'm going to use that to fill in the gaps, so on and so forth. But the key phrase in this question is a more accurate representation. What do we mean by a more accurate representation? So a more accurate representation could be active exploration, where what you're trying to do is you're trying to spend your budget to grow your network, to observe more nodes and edges. The other thing you can do is active learning, where you want to grow your network, but only so as to learn the best performing function for a task down the road that you're interested in. And that task, for example, could be selective harvesting, which is what I'm gonna talk about. And so we call this the task-driven network discovery. That is, you know your network is incomplete. You know you're partially observing the phenomena of interest. You want to grow your network, but you want to grow your network for a particular task. And so what is selective harvesting? So selective harvesting is as follows. You are given a seed network, G0, and a budget. Again, you do not have all the budget in the world, so you have some constraints. And you want to grow your network, but you want to grow your network to discover as many nodes of a particular type. So for example, when I was discussing this work with the clinic in San Francisco, it was that you want to grow your network to bring in as many, in that case, people who have a particular sexually transmitted diseases. And so what you have is you have your seed network, you know who has a disease or not, for example, you have this boundary network. And what you can do is you can query a particular node to ask for its label and also for all of its neighbors. So you don't get the labels of the neighbors. What you do is you get the label of the node you queried and all of the people that that person came into contact with. Now, of course, there are lots of different access or discovery mechanisms. And in previous work, my lab has worked at, well, what if when I query, I just get a random edge? Or what if I get k-random edges, or lots of different kinds of access mechanisms, which are tied to whatever API or whatever mechanism you have to get more information. And so here, the goal is I have this boundary set of nodes, which node to query. And one of the things which is interesting is that I want to query a node that here, for example, will have a label of 1, but I also want to query a node that will bring to me as many nodes, or will be the root of a tree that will bring to me a lot of nodes that have label 1. So there are lots of issues that make this problem difficult. One is this sparse labels, right? So you oftentimes will see very few examples of the relevant structure that you're interested in. There are network effects that you perhaps need a macro view of the complex network to be able to actually learn what you want to learn. There are these multifaceted notions of relevance. Perhaps I will query somebody and their label is 0, but they will lead to lots of people who have label of 1 here. And then there are lots of other complexities in terms of the invariant features that you're seeing in the network, in that you perhaps need to see lots and lots of these topologies to be able to understand the relevant features. So one of the things that we wanted to do was to look at the selective harvesting from a reinforcement learning perspective. So not do a supervised learning approach, but do an RL approach where I have this agent that will interact with the environment, and based on its actions, it goes from one state to another state and then gets a reward. You all know reinforcement learning. And we were looking at this as a Markov decision process. We didn't look at it as a constrained Markov decision process, and we haven't looked at it in terms of POM-DB. What are all the elements of a Markov decision process in our setting? So the first one is the state space. So for us, the state space is the state of all graphs over the set of nodes that you have. And so as you can imagine, this state space is very large. And the way that we model the state space is by actually looking at a set of random graph models among the set of nodes. So you can think of random graph models like Erdős-Rényi, Barabasi-Albert, hyperbolic, Kronecker, block 2-level Erdős-Rényi, so on and so forth. And then, of course, you have a labeling function on a particular node in terms of whether the node is 0, not of interest, 1 of interest, or I don't know, which is represented as a star here. So when I move from one state to another, I'm actually moving from one graph to another graph. You can think of it as, oh, well, maybe I could like represent this as moving from one node to another node, and we can talk about that in the breakout room. But for now, each state is a graph in itself. So then the actions are the set of boundary nodes that you have, right? So that's your action space. And so when you act, you're picking one of those nodes in that boundary set. The transition function is the probability of going to a new state given this state and the action that you pick. The reward function is whether by querying this particular node, you got a node that was of interest, whether you got somebody that had a particular disease that you were interested in or not. And then in terms of the policy, right, so we're trying to learn a policy. As you all know, it's a function of a state actor. And we're learning the probability of going to a new action given a particular state. And so what we have is we have these instantiations of policies over a particular trajectory. And a lot of what we did in terms of this offline learning, which I'm going to talk about, is actually generating these examples over these paths. And the one thing was that whether even generating these kinds of trajectories over random graph models are going to be helpful or not, right? Whether it's useful if I learn lots of weights and parameters on these kinds of synthetically generated trajectories. And you'll see that it is useful. Otherwise, we wouldn't have a paper. And of course, you have a budget B in terms of how long your horizons can be, how many questions you can ask. And so in terms of modeling the future reward, it's just a cumulative discounted reward over the length of your trajectory, which you all know, and no problem there. This is a simple example of it in terms of growing this graph and looking for nodes of a particular type. And of course, we have a value function. This value function takes a state and returns the expected discounted sum of the future rewards. And the goal is to maximize the value function, right? So find the policy that will maximize the value function. And of course, we have a Q function. So what we do is we decompose the state value into action-specific values. And so in terms of the value function, then what you're doing is you're summing over all of the actions. You're saying what's the probability of an action given a state, and then what is this action value function, which again is the expectation over the policy of the cumulative discounted reward that you're going to get given the state and the action. So what current approaches are missing is we were especially looking at online approaches. One of my PhD students, Tim LaRock, has an online approach. And one of the issues with just looking at online approaches is that you're not going to see enough training examples to be able to learn what you want to learn. Oftentimes, you get this tunnel vision. You do not see phase shifts in your reward signal. So for example, if you have a network that's incomplete and you're interested in these like dense subgraphs, and the dense subgraphs are not near each other, then you may get lost when you go from one dense subgraph to trying to find another dense subgraph. And in fact, this is what we saw with online approaches here. And so this is just a dig on online approaches, that we didn't find that online approaches were competitive to approaches that are hybrid in terms of offline plus online. And so that was our charge at this point, was that can we learn strategies in terms of offline learning on various tasks and topologies, and whether learning on these random graph models like a stochastic block model, so on and so forth, is that valuable, or am I just wasting time? And so the first thing that we hit was, how are you going to represent your state space, right? And if you remember, every state is a graph, And of course, here we could have gone with lots of different graph neural network approaches. But one of the things that we wanted to do is, as opposed to like picking one graph neural network, and as I'm speaking, probably like 10 people are writing, their own favorite graph neural network approach. We were like, let's think about what kind of embeddings are helpful for this selective harvesting task, because the selective harvesting task seems to be very important in real world applications. So instead, what we tried to do was, I'm going to represent every graph as an embedding. And then in terms of learning, you'll see in a minute in terms of what we do for the learning. So I won't give you that spoiler. So every state is a graph. And what I want to do is I want to embed that space. And one of the assumptions that we were making is that some states, that is, some graphs are more helpful in helping us estimate these value and policy functions compared to other states. And whether there are like certain graph embedding approaches that will be helpful to us in this selective harvesting case. So what we do in terms of how we're going to represent each state, which again is a graph, is we're going to embed the graph. We're going to reorder the nodes. Remember, these graphs can be very large, right? If you're dealing with, for example, contact graphs or other types of real-world networks, you can have millions or billions of nodes. So what we do is we embed the graph. We reorder the rows of the adjacency matrix, obviously the rows and the columns here, so as to have a prioritized list of the boundary nodes, and then we truncate the adjacency matrix so that we have a smaller representation of the bigger graph, and only the part that we think are going to lead to better nodes to query. So the way the state representation again works is you take the graph, which is your state, you embed it, you reorder the rows and the columns so that you get a prioritized list of the boundary nodes, and then you truncate the adjacency matrix. So when you do the truncation, you have this hyperparameter K, which basically, depending on your computational resources, you can increase the K, which is a bigger adjacency matrix, which means bigger set of trajectories that you have to look through, or you can make K smaller. In the experiments we ran, a K of about 256 was fine. We tried only powers of 2. So then in terms of training, right, this is all offline training. And then the idea is that, is this offline training good for anything? So we looked at a bunch of background models. So this is like stochastic graph model is the background that I'm operating on. And then the foreground model is the target nodes that I'm interested in. So for example, you can pick stochastic block model, and then you can generate a whole bunch of BA networks and embed them within the stochastic block model, and then train on the trajectories from that, and then see if what you have learned there can be helpful as you move along. So that's how we will generate all of these training instances, again, by picking a background instance at random. Obviously, all of these random graph models have their own parameters. Then you pick a foreground model. Those also will have their own parameters that you will set in terms of, for example, number of nodes, a probability of connection, so on and so forth. Then you insert the foreground models into the background models, and those are going to be the graphs from which you're going to extract your trajectories. So then what we're going to do is, given that these are graphs that we have created, we have the ground truth for them. And so we can then have this training set where the input is the state action pairs, and the output that I want to learn are the rewards. And then the learning objective for us is to find a policy that will maximize the objective function, right? And so the objective function is summing over all the states, the probability of being in that state given that policy, sum over all the actions, probability of being in that state given that action. Then you have your exploitation term, which is the advantage of doing a particular action. And then we also have an exploration term, this notion that, oh, this is a state that's novel, that I haven't seen it before. And perhaps this novelty is a good thing for me to look at, because it will allow me to learn something that I haven't seen before. And then we learn the weights, the parameters based on a proximal policy method. And so the model that we have is called the Network Actor Critic, where the actor will generate these samples. The critic will then judge the samples and give the estimated advantages to the actor, and then the actor will update its policy. And so you go through this round and round. And of course, within reinforcement learning, there's the actor critic network. So that's where we borrowed this actor critic business. And just as a side note, for our policy and the value functions, we just use a CNN with 3 convolutional layers and 64 hidden channels and a final fully connected layer. The goal here was not, oh, let me try GCNs and GATs and so on and so on and so forth, right? The goal was, okay, is this even doable? We can extend to those later. So in terms of our competitors, we did comparisons with methods that don't do these kinds of sequential planning. So one is this D3TS, which is a multi-arm bandit approach, which uses some Thompson sampling to select from the boundary. We use just an online learning approach and then some basically baseline heuristics. And so these are on synthetic networks where we embed these dense subgraphs, and we want to find these dense subgraphs. And one of the things that happens with all the other approaches that do not do this offline learning is that when they find one of the dense subgraphs, they can't find the other one. And so they get lost. It takes them a long time. So here on the x-axis, you're seeing the number of queries, which is your budget. On the y-axis is the cumulative reward. And so NAC is able to find the other anomalous subgraph. We also ran it on real world data. These are Facebook pages. And in terms of the target nodes, we embedded these small subgraphs with density of 0.8. And again, NAC is the blue line. And you're seeing in terms of the x-axis, which is number of queries, and the y-axis, which is a cumulative reward, is that we're able to do better than the other ones. One of the examples that was interesting, we ran it on the live journal data set. So we ran NAC on the live journal data set, and then other approaches on the live journal data set. This was a bigger data set with about 4 million nodes and 34 million edges. And here for the target attribute, we picked one of the attributes from the live journal. Basically, the attributes are group memberships, and we picked one of the group memberships. So here you're training NAC on something that you don't know what the process is that's actually generating it. And one of the things that we see is that as our budget increases, actually NAC, which is the blue line, so higher again, it's better, that's the cumulative reward, we are able to learn how to ask queries to get these nodes that have the top group in them, even though that is not what we learned about. That is, as you see lots and lots of these offline trajectories, that gives you enough of a knowledge to then basically transfer to another setting where we don't know what processes are generating these target attributes. And then lastly, I said there was this notion of the embeddings. And so we cared about like which embedding is going to do well. And in particular, like if the target network that you're interested in is already embedded in what you saw, then that is easy. If the target network is not is far away from what you're seeing, like this middle example, then that's much harder. So think of these as like adjacency matrices. And then if the target network is adjacent to your seed network, then that also is easier. So anyways, we tried various ways of measuring different embeddings and how well they do. I don't have time to talk about all of them. I'll just talk about 2 of them. And so here I'm just showing you basically how hard it is to find this dense subgraph versus the background density is on the x-axis, the anomaly density is on the y-axis, and the color is the area under the curve with the various embedding approaches. So we used personalized PageRank, MOD, which is just based on highest degree, GLE, which is based on geometrical Laplacian embedding, just a simple Laplacian embedding, PCA, which has been around since forever, and Node2Vec. And one of the things that you see is that it's easier, you have higher AUC values if you use personalized PageRank. And this is interesting because Stephen Gunneman's group at TU Munich has recent results in terms of perhaps using personalized PageRank is good for graph neural networks. You get better results. And then also, if you use personalized PageRank, on the x-axis, you're seeing number of queries. On the y-axis, you're seeing cumulative rewards. Obviously, the higher up you can go, the better it is. The different colors are the different episodes. And so with PageRank embedding, you reach higher cumulative rewards with lesser episodes. So you converge faster for the selective harvesting case. So just to wrap up, I know I'm a couple of minutes over. Thank you, Pitar. So basically, we looked at this problem of, okay, I have a network that's incomplete and I want to grow it for selective harvesting. And this table basically like gives you a perspective in terms of like where we are based on some of the things that we compared about, and also based on this work by you is in Yuri Leskovich's lab, and they looked at growing these very small chemical networks. And then lastly, one of the things that we're doing is we're using this approach now to control pandemics. So you have the complex network effect in terms of mobility networks and contact networks. You have partial observability, and you have the large decision spaces. And so with Rajmonda, again, we have this system called COANET, which does the modeling of the mobility network, the modeling of the disease, where at every edge we have the parameters of the SEER model, we have a reward function, and the optimization component there is actually online learning. We haven't found a good set of offline learning trajectories there. It's a very highly dynamic approach as opposed to like the examples that I mentioned before. Thank you very much. I know I'm a couple of minutes over, and I'm happy to take questions.